While exploring a large cave, a spelunker finds herself in a large chamber where she can't see the ceiling. She carefully sets up to measure the average time it takes for water droplets falling from the ceiling to fall the last 3 meters above the floor, and statistically determines, in other words, very precisely, based on a statistical analysis, determines that the time is 0.135 seconds. You can appreciate why she might need to be precise because that's a very small time, and if you have imprecision in that, it might affect her results a lot. What height does this result indicate for the large chamber, assuming the time correctly describes the final 3 meter fall time for a water droplet that fell from the ceiling starting at rest and at a constant free fall acceleration of 9.81 meters per second squared? Notice that with that last assumption there, we've kind of implicitly thrown in here, we're neglecting air resistance, because if there were air resistance, the constant free fall acceleration of 9.81 meters per second squared wouldn't necessarily hold. So this is actually a very non-trivial, also very not realistic example, I think, but I've tried to make it somewhat plausible in the way I've worded it. But it's meant to challenge us a little bit in using kinematics to solve a very non-trivial type of question. And so if I look at like the fall of one of those water droplets here, whoops, sometimes my pen doesn't quite, okay, there it goes. And then I'm going to look at like here the last 3 meters. I like to put a little mark there to say, okay, so that represents 3 meters above the ground. And the only thing we're really given is the fact that that is 3 meters and that the time for that is 0.135 seconds. So this is kind of a two-process problem because the thing that we're really asked for is the overall height of this chamber and that this water droplet has fallen through. What I'd like to do to kind of set this up in terms of variables, though, is I'd like to look at the height above those last 3 meters and define that to be h. And then recognize, so like I'm going to say, let's see if we can figure out what that h is. But then realize that the answer to the question that we have posed for us here will be equal to h plus the 3 meters because I kind of took that out. So I'm just going to write a note to myself about that because I might forget otherwise. Now, a challenge with this question is how do you get h? Well, directly. I don't think you can. But what you can do is I can go and look at this as two processes. There's a process of it falling from the ceiling to here, to 3 meters above the floor. And then there's the last 3 meters it takes 0.135 seconds. And if I look at, I'm going to look at that as like process number 2, and this is process number 1. And I'm going to start by looking at process number 2 and recognize that, so I am given, I think, there a delta x that is equal to 3 meters and a time that is equal to 0.135 seconds. Wouldn't it be neat if I could find what the initial speed for that is? In other words, if I could answer this question, and how might I go about doing that? Well, the first kinematic formula is delta x, I'm going to use the delta form of it, is equal to v naught t, and normally it would be plus 1/2 a t squared, but I'm just going to say that it's plus 1/2 g t squared. Now, somebody might cry foul on this and say, wait a minute, shouldn't, if you put in g, shouldn't it be minus because things usually fall down? I'm going to make the implicit assumption in this problem to make things simpler that down is positive. If I did the opposite, it turns out my displacement would also have to be negative, and I'd put the minus sign here, and I'd probably also have to put a minus sign on this delta x that I defined to be equal to a positive 3 meters, but it really displaced a negative 3 meters, right? So I thought it was simpler to maybe make this assumption here, and then recognize I can divide through everywhere by time, and then isolate v naught, and I wind up getting that v naught is equal to delta x over t minus 1/2 gt. And then if I plug in the numbers of 3 meter divided by 0.135 seconds minus 1/2 times, oops, let me make that 1/2 look a little bit better, 9.81 meters per, this is the part where tracking all the units does get a little inconvenient, I'll admit, but I'm doing it anyways. Times the, I've barely got enough space, or maybe I don't. Let me see, 1.3 or 0.135, I meant to say, seconds. We're solving for V naught again, so this should all be as some number in meters per second. It's definitely calculator time now, so I've put that into my calculator, and I get, like, let's see, 21.56. I want to watch out with round off error on ones like this, but it's like 56 and then double zero before anything else. So since we're at 3 sig figs and I want to maybe be at 5 to avoid round off error, I'm just going to put another 0 here, meters per second. So that gives me the final velocity there. Now I'm going to look at process 1. So what I'm trying to show with this example is how you can do two processes. You can kind of separate them a little bit, because I'm going to look at the second process and say that really what I've just found here is the final velocity is equal to 21.560 meters per second. And the thing that I'm trying to find is this thing I called h, right? I'm solving for this thing h, but h really kind of represents like the delta x for this process. I'll go ahead and call it h just to not mix it up with the other delta x. In terms of kinematic formulas, though, I feel like maybe the best one to use here, there's no time involved with this process number 1. So maybe the fourth kinematic formula is the way to go. But I'm going to replace this delta x by an h. So we'll make that an h in a minute here. And that's the thing that we're solving for. Also recognize that the initial velocity is equal to 0, so that implies that really I've got, for this problem, I've got v squared is equal to 2ah, which means that h is equal to v squared over 2. Actually, I said a, but really we're talking about free fall, so maybe I can go ahead and also like replace that with a g, right? So I'll just make that a g right here. So v squared over 2g. In other words, as numbers, I'm going to put in 21.56. We'll just pretend the zero's there, meters per second, squared divided by 2 times 9.81 meters per second squared. And then I'm going to put all that into my calculator, and my calculator says that that is like 20, let's see, I'll round this one off because all I'm going to do is add 3 to it. This is at 3 sig figs, 23.7 meters. And so that means since my answer has to be that plus 3 meters, my answer is going to be 26.7 meters. Given how convoluted this all is, it's probably appropriate for me to box that answer in case anyone didn't follow this whole video, that they'd at least be able to see what my answer is in that box right there. And we can check it with the slide and see that that is correct.